As you know, chemistry is the study of matter and the transformations of matter. In the series of videos that we begin now, we start to investigate the transformations of matter. One of the most important ways that matter has to transform is through chemical reactions, in which you're going to have some set of reagents, and then you will generate some set of products. Here we have a totally generic chemical reaction with two reagents and two products, but we're going to study a variety of chemical reactions. Now, this series of videos is about the concept of stoichiometry, which is something that is going to allow us to quantify exactly how this transformation takes place. Questions that we're going to be asking are, well, if I have 1 gram of A, how many grams of product C will I get, for example? Okay, so we're going to start by providing some initial foundations to those type of calculations, and this video is concerned with the atomic mass. Okay, in the end, even though the transformations that occur between compounds are atomic at a fundamental level, right? So atoms exchange other atoms that are coordinated to or bonded to. Okay, in the laboratory, we're worrying about weighing compounds, right? So we weigh an amount of A or B, and then we generate products C and D, and we have to weigh those as well, right? So we actually have to worry about the concept of mass and how is that connected to atoms. All right, so then we're actually going to define now what atomic mass is. All right, by definition, okay, we have agreed on a set of masses so that we can actually have masses for all of the periodic table. And the convention is as follows. We're going to say that one atom of carbon-12, okay, this isotope, carbon-12, one atom of carbon-12 weighs exactly 12 atomic mass units. Now, this mass is exact. That means that you have an infinite number of significant figures right here. Okay? Some books actually use here the notation U as AMU, but I prefer to use AMU as atomic mass units. Okay, that is the weight of just one atom. And as you can imagine, that is a weight that is very, very, very small when you actually use it in kilograms or in grams. Okay, as a matter of fact, what we actually know is that one atomic unit, one AMU, the conversion to kilograms is equal to 1.66 10 to the minus 27 kilograms, right? So it's a ridiculously small mass compared to microscopic objects, but that's how small an atom is. Now, this mass is important because it sets the reference for the rest of masses that other atoms might have. For example, if you study the carbon-13 isotope of carbon, so still C6, but now you add one more neutron, it turns out that now we can actually weight what is the weight difference between this carbon and that carbon, and then come up with the idea or with a number 13.0034. Okay, AMUs. Okay. Now, so this, like this, you can get weights for every single isotope in the periodic table that exists, and now we actually have to worry about the periodic table. When you actually go to the periodic table that you have in your books or online, you find that when you look at the element carbon, okay, it actually tells you that the atomic mass of that particular element is 12.01 AMUs. The question is, well, where does this mass come from? Notice that this can't be C12 because C12 weighs 12 AMUs exactly, and it can be C13 because C13 weighs more than 13 AMUs. So where does this number 12.01 actually come from? Okay. Well, so it turns out that this is what we'll learn to do in this video. It turns out that the weights that you see in the periodic table correspond to a weighted average of the atomic masses of the naturally occurring isotopes of a particular element. Okay? Carbon actually has 3 naturally occurring isotopes. You have C12, C13, and C14. Now, C14 is completely negligible because the natural abundance is extremely low. There's only one atom in every trillion atoms of carbon that is actually C14, right? So the only ones that are reasonably abundant will be C12 and C13. Of those two, C12 is much more abundant than C13. If we actually read here the natural abundances, okay, we find that C12 happens to be 98.89% abundant. And then C13, which again is 13.0034 AMUs, is 1.11% abundant. Again, there's also C14, but it's, the weight here would be ridiculous, okay, much more than that. Now the question is then, how do we actually then define the mass that appears in the periodic table, right, for carbon? Well, if you have these two isotopes, and these are the abundances, the mass that you see in the periodic table, again, is a weighted average of these masses, and the weights that you use for the average are the natural abundances. Okay, so we can write here an expression, which is the atomic mass, okay, which again is what you see in the periodic table, is going to be equal to the weighted average of all of the isotopes. So that would be the mass of the isotope I multiplied by the fractional abundance of that particular isotope, abundance of I. Okay? Where fractional is the same thing as percent abundance, but divided over 100. Right, so let's actually crank here the numbers for carbon so that you see where this comes from. Right, so the atomic mass for carbon would be the mass of, we have two isotopes, 12 and 13. The mass of carbon 12 is 12 AMU exactly, and the fractional abundance is 0.9889. Okay, and to this we simply add the mass of the carbon 13 isotope, which is 13.0034, okay, multiplied by the fractional abundance, which is 0.0110. Okay, and when you do that, you find that this is equal to 12.1 AMUs, which again is what you see in the periodic table. Okay, so again, when you go to other elements in the periodic table, you will find masses that don't belong to a particular isotope, unless there's only one isotope for a particular element. But in most cases, what you will have is that mass will be the weighted average of the naturally occurring isotopes for that particular element. Okay, so in this video, we have defined the concept of stoichiometry, the goals of this set of videos that we start now. And we have defined where the reference is for the atomic masses, that is the carbon-12 isotope. And then we also have defined what the atomic mass is that appears in the periodic table.